to introduce, uh, before we move into the session, I would like to introduce our guest speaker today. Thank you very much for accepting our invitation, Dr. Leon. So Dr. Leon Fernando obtained his BSc Honors degree in Physics, University of Sri Chavathanapura in year 2010. He completed his Masters in Engineering in Nuclear Systems Safety Engineering, and he completed his PhD at Nagoya University, Technology Nagoya, Niigata, Japan. In his career, first he appointed as a teaching assistant at the University of Sri Chavathanapura in year 2010. So after that, he joined as an assistant lecturer to the Department of Physics, University of California. So finally, he joined to the Sabaragamuwa University. Now he is a senior lecturer in the Department of Physical Science and Technology, Sabaragamuwa University of Sri Lanka. So he is serving as a reviewer for the several journals. So he is one of the reviewer for Applied Science Physicality, Scientific Instruments, Helene Journal. Also, he was awarded as Outstanding Reviewer 2021 for the Journal of Applied Physics D. His current research interests included the applicability of atmospheric pressure plasma in bioapplication, computational physics, supply chain management for disaster relief operations, and nuclear physics and safety systems. So today he is going to present atmospheric pressure plasma and its applicability. So I would like to welcome our guest speaker, Dr. Leon Fernando. Over to you, Dr. Leon.
Thank you very much, Dr. Vasanthi, for the nice introduction. And I hope everyone can hear my voice. So if anyone having trouble in listening to me, please let me know. So I will move to the today's session. So today's session actually about the atmospheric pressure plasma, and this area is new area to our country. So because I have some interaction about the atmospheric pressure plasma, so I think that Sri Lanka also can be benefited a lot with this technology. So so the presentation, the flow of the today's talk will be like I will going to introduce about what is the plasma, how we can generate the atmospheric pressure plasma, and kind of my study, like what I did, like why it is this area we can use that one. So before we move into that one, like I will give you some idea about like what I did using this technology, so which is related with the biological application. And also I will show you like which areas that our country having a problems and which areas we can use this technology to overcome those problems. So first, like I will tell about the plasma, right? From our school time, like we learning about the three type of matters: solid, liquid, and gas. But more than 90% of our visible universe is consist of the plasma state. So the plasma state mean like when the gas, when they absorb more energy, they become ionized. So we're going to have the negative charge particles and also have the positive charge particles. So when they separating together, they joining they generating the state called the plasma state. So in figure also, like you can see that what is the general idea of the plasma, right? Then I will move to the types of plasma. Like when we come into the plasma, there is many type of plasma. Like in this figure also, you can see that there is some type of things like the solar corona, our sun, the neon signs, the fluorescent light, flames, lighting, the aurora, solar wind. Like we heard those things, right? Do everything which is staying in the plasma state. But in our country textbooks or in the university level, we might not have a much detailed idea about these things. So that is why I want to introduce this one more and make the interest in our country. So when we come into such a plasma, we can separate the plasma into mainly two types, like thermal or the hot plasma, or non-thermal or cold plasma. So in the thermal plasma, normally we are saying everything is in the thermal equilibrium. Like in here, you can see that the TE, TXE, TG, like it's saying that the temperature values, the electron temperature, the movement of the electron, because of that one, we defining a temperature value. And where when we having some kind of a gas, like it's showing some excitation, right? So the excitation temperature and the gas temperature. Normally in the hot plasma, due to the thermal equilibrium, everything in a equilibrium state, like every value is same. So normally they increasing into a larger temperature values, like you in this figure. Also, you can see it is in the 10 to the power 6, 10 to the power 4, 10 to the power 8 values. But coming to the cold plasma, this thermal equilibrium is breaking. So we're going to have a non-thermal equilibrium. So because of that one, electron temperature is higher than the excitation temperature, and the gas temperature is lowest. So when the gas temperature means the normal temperature, that what we're going to feel. So the plasma, the atmospheric pressure plasma, normally we are saying it is in the atmospheric condition. Normally the temperature values will be in the room temperature or slightly higher than the 20 Celsius degrees. So it is a kind of a thing that we can use. So before that one, right, more details, like I will tell something about the hot plasma. In the hot plasma, like we have in the experiences of the hot plasma, the lighting is a kind of hot plasma. And in the arcs, like when we do in the welding type of things, also like we have in the electric arcs, like it also kind of a hot plasma. Then in the universe, like most of the things, like the dwarfs, solar core, like we are telling those things as a warm dense matter. Everything is staying in a hot plasma condition. So the temperature values are very, very high. Right. So here you can see that in the log scale, also like in the y-axis, you can see that log to the t to the power is like 2, 3, like it is a very high value. But there were some studies now in investigating the universe things, like they also generating the warm dense matter in the laboratory conditions. But I'm not going to talk about that one, because my area depend with the cold plasma. When coming to the cold plasma, like we have two techniques. One is low pressure plasma. So that means like we're going to have a chamber with a low pressure. Now, when we making a low pressure with a certain gas, what we are doing is like we are reducing the collision between the molecules. So because of that one, the temperature values are decreasing. And another thing is the atmospheric pressure plasma. That means in the open air, we are generating the plasma. So in the figure 6, also you can see that when we have in the atmospheric pressure plasma, like we can touch that one, right? Because the temperature values are in the room temperature. So it is not affecting to our skins so much, like it is not increasing up to the 60 Celsius or something to burn our skin. So yeah, we can use such a things, because using this plasma, the important thing is we can generate the chemical species, excited and the ionized chemical species. Because normally when we developing some applications, we want the chemicals to have interactions. So normally we are using organic compounds, inorganic compound, mixing with that one, like we are developing a new type of things. But rather than using the external chemical species, we can use the open air chemical species. But we know that in the open air, like we have neutral species, but using the plasma technology, we can make those atmospheric particles into charged and the excited species, right? So in the next slide, like in here, I'm telling about the atmospheric pressure plasma. Like here the pictures about some of my work, like it is a plasma jet, like I will discuss in the later. But when we generate in the atmospheric pressure plasma, we are generating everything in outside, so we don't need any vacuum changes. So the cost of having the vacuum changes, we can eliminate that one, because in the open air, if you're having a working gas, if you're having the the equipments that we needed, like it's like the dielectric barriers, then we can generate the plasma in the open air, right? So it is a easy technology. So that is where we can go as a country. So we can spend our amount of money that we are spending for the equipments for our vacuum changers. We can reduce that one, and we can open we can do the experiment in the open air. We can generate the chemical species in open air, and we can try use those chemical species with our application. Now in the next one, like I will tell, like, okay, if we going to make a atmospheric pressure plasma, we are saying that dielectric barrier discharge, or the DBD technology, is using. Now in here, the figure 9, it's showing the systematic schematic of that kind of a setup, DBD setup. Now in here you can see there will be two dielectric barrier charges will be connected to an electrode. Now when we're applying a high voltage, what is going to happen? The working fluid, normally that working fluid may be a noble gas or open air or a mixture of the gases, like we can have a many type of things. But when we have a certain amount of electric field, the gas, the working fluid, going to discharge, and they try to generate their self-sustaining electrical field. So with that one, they try to keep maintaining the plasma discharge in open air. In the next slide, in the figure 10, you can see the plasma jet, because that is where I'm also moving. Like in the DBD technique, like we can generate like a kind of a constant non-moving plasma, but using the plasma jet, like we can make sure that plasma traveling into the open air. When we make that the plasma propagate or the moving into the open air, they can have an interaction with the air molecules and can generate more and more chemical species. So there is many techniques of generating the plasma jets. So few of them are listed in here, and later I will also discuss about their braking mechanism and also the type of the plasma jets I developed for my research work, right? Now in here, when we're discussing about the self-sustaining part, the breakdown voltage and the current is very important thing. We know that increasing of the voltage also increasing the current value. Now in here, you can see a graph that it is corresponding to the voltage and the current. Now if you see that one, after the saturation regime, like then we are also saying the Townsend regime, then when it's coming, like, okay, the voltage will, when we increasing the slightly, the current value is try to increase largely. So there will be a certain voltage and the current value which is happening, which is breaking the working fluid. So we are telling that one as the breakdown voltage. Then after that, even though we decrease the voltage value, the plasma, because of the discharge, we have in the now two charge particles, like the negative side and the positive side. So they maintaining kind of a voltage, the electric field, to maintain that plasma condition. Then again, with a increase of the voltage, we can see that the current also increasing. Now with these things, we can separate into three type of plasma discharge in the atmospheric pressure plasma. One is arc discharge. So normally the light in also, like we know that it is happening in the open air in the atmospheric condition. So but in the lighting, we are saying as the arc discharge. So the current value and the voltage value is very high. Then we have in the glow discharge. Normally my research field is with the glow discharge section. So the neon sign, the fluorescent light, they also coming under this one. Then we have in the corona discharge. In the corona discharge, we like corona term, we are very familiar nowadays, but the corona discharge here mean like we also having the experience, like when we going when we walking in the road, sometimes near the current line or the electrical lines, we are hearing some kind of a discharging sound. But if you see in the night time, like we can see some kind of like the purple color is something happen around the conductor wires. So it is a corona discharge because it is happening on a conductors, like in a small, on a like we are saying as the localized areas. It is not continuing, right? So those kinds of discharges we can separate it according to the current and the voltage behavior. Now, breakdown mechanism of the atmospheric pressure plasma jet, like we can use the different type of electrode configurations. Because of that one, the breakdown mechanism also changing. Now in here, like the figure 12, you can see that when we have the one single active electrode, when we give in the power supply, at that certain point, we can generate the discharge. So because of that one, for the upstream direction and the downstream direction of the working fluid, like the plasma discharging is happening. But normally, like in this figure, maybe it's not clear, but the downstream jet is little longer comparing to the upstream jet. Then we can have we can maintain the double electrode. Now, when we have in the double electrode, like what we are doing is like we are placing a physical ground electrode inside the dielectric barrier. Like the dielectric barrier here mean like these two capillaries, they acting as a dielectric barriers. Now, because of that one, when the discharging is happening in the inside of the tube, they feeling kind of a physical ground voltage. So the charged particles, they try to go to that physical ground electrode and try to discharge, right? So with that one, we can increase the jet properties. And like then we have in the parallel electrode. So we can use these kind of a mechanisms to generate different type of the plasma jet. Why this one is, the understanding of this one is very important is like, if we're going to use these as applications, then it is very important to have an idea about what is the mechanism, the breakdown mechanism, how we going to generate the chemical species which we needed for the applications. So now from now, I think you will have some kind of idea about the plasma and the breakdown mechanism and the generation mechanism of the atmospheric pressure plasma. Now I will give some idea about the use of this atmospheric pressure plasma in bioapplication, which I did as my research work. Now, why we need the atmospheric pressure plasma with my studies, like nowadays the medical field is going to a new area. Earlier, we know that if we got sick, like different type of medicines and those things are investigated while our body is still there. Or sometimes if it died, like they doing many tests to identify what type of disease that we are having, what kind of drug we can develop that one. But nowadays, to overcome these things, like we want to grow the cells in the laboratory condition. Then we can change the genes, or we can test the new drugs in those cells. Then if it is success, then we can implant to our body, right? So I don't know whether you heard or not, like in few years ago, the Nobel Prize for the chemistry, it was received for such a study. Now that means like they find a cure for the Parkinson disease. That means the scientist is able to grow the neuron cells inside the laboratory after 6 years of the failing, right? Finally they succeed that one. Now this area is developing, but when it is developing, they use they want some kind of a mechanism or kind of a platform to grow the cells, right, in the laboratory condition. So they having some issues in here. When the scientists want to have a cell culturing inside the lab, they need some kind of a device which is facilitating the cells interaction, cell substrate interaction, and the microenvironment of the cells, right? So to facilitate that one, they identify some of the type, and in here I listed only one, which is the polydimethyl siloxane, which I use with my study PDMS. So it is a non-toxic, chemical inert, like, so it is not affecting when having the cell-cell interaction. But there was a problem when we use in that one for the cell culturing. The problem is the surface is hydrophobic. So that means it is like a lotus leaf, like when the cell culture, they having the other properties, like it is facilitating the cell-cell instructions, but they not providing the cell substrate interaction. So the attaching and growing in the laboratory, it is a problem. So what they earlier done was they change the surface by exposing to the low pressure plasma. So when we doing that one, like they use the mask because they want to control the area of the cell culture. Now with that one, like we can see that the hydrophobic condition change into the hydrophilic, right? But the problem is like there was the wetting size we cannot change, and the mass charging also happening. So controllability of the cell culturing areas is have a problem. Now in this study, when even though they use the low pressure plasma with the mass, what is happening here with the plasma is like the hydrophobic, like in here, if you can see the silicon structure, which is having the CH3, right? They were replaced by the oxygen species. So in here, like for the plasma treatment, when we using the low pressure plasma with the mass patterning, like what I am telling here at that point is like using the plasma, like we make some chemical reactions, right? So CH3 in that PDMS surface was replaced with the oxygen species, right? So without introducing any inorganic or organic chemical using the plasma, we make that change. So why now when we doing that one, like we had a problems like with the low pressure, we can control this one. It is a problem, right? Then we cannot move the place of the modification. To overcome this one, like we suggest that why we not use the atmospheric pressure plasma and why we not use the atmospheric pressure plasma jet. So we can make a point irradiation, right? So when we checking that one, like we need to check like if you're going to use the atmospheric pressure plasma or atmospheric pressure plasma jet, we need to consider some of the parameters, because according to your application, these parameters are important. You need to identify which one is the most suitable one. Then, so I listed some of the parameters that I investigated when I'm developing my plasma jet. Right. So here in this figure, there was some plasma jet configurations that I used. Parallel electrode, also I investigated, then double electrode, and with a double electrode with a floating pin. So with the floating pin, we want to make that in the atmosphere, when the plasma or the charged particles, when they're propagating, they're feeling the virtual ground voltage. But other than the virtual one, we want to include a physical ground voltage. So that is why such modifications were done for the double electrode configuration. So with that one, we observe that the plasma jet length is changing, that comparing to the parallel electrode configuration, double electrode configuration, showing a larger, the plasma jet length increase. Now, for my application in that time, because we are using with the cell culturing, so it is very important to having a larger plasma jet length, because we can place our samples of the which we want to cultivate or the surface modify away from the electrode. Because if we come very close to the electrode, we might have a sudden corona discharges. So it is very not suitable. So that is why we want to have a longer plasma jet length. So that is why our application, we investigate such electrode configuration. And also when we have in the additional pin electron, the floating pin electron with the ground condition, we observe that there was a secondary discharge other than the DBD, like inside the capillary, other than that one, due to the ground electrode of the physical ground electrode that we are providing in the atmosphere, we can have a secondary discharge. Because of that, the chemical species showing a sudden increase in their density. Now, from the optical emission spectroscopy, we are getting the idea about the what amount of chemical species will be there and what type of chemical species in there. So in here also, in the optical emission spectra, you can see that in the black color line, that is we are taking 9 millimeter above the additional pin electrode, but the blue color line is at the additional pin electrode. So we can clearly see the sum of the excited and the charge ionized particles, the intensity is increasing, and also jet length also we can able to increase. Then we check the flow, that when we're providing a gas flow or the working fluid flow, it is changing the behavior. So laminar to turbulent behavior we can observe to change, and it also depend with the flow rate, also depend with the capillary tube size. So in our application, like later you can see that I'm going to show that one, like in the laminar regime, that means when we're having a smooth flow, the generation of the charged particles or the chemical species is very high comparing to the turbulent flow. Even though like in these figures, like the turbulent flow, it is showing the larger width plasma jet and those things, but the interaction with the atmosphere of these charged particles is very low comparing to the laminar regime. So the A and the simple B one, like they depending, like they corresponding to the laminar regime according to this capillary and the flow rate. So here you can see that it is having kind of a nice, like the pinpoint shape. So we make the calculation using the Reynolds numbers also to identify, okay, which value should come, which flow rates should become in the laminar regime and which is coming to under the turbulent regime. So with the flow rates we are having with the tube capillaries, we observe that the 2 liters per minute flow rate is suitable for generating the very smooth plasma jet. Then, as I said earlier, now in here, it is showing the figure of the chemical species distribution, like from the starting from the capillary exit point, when the charged particles or the discharged particles, when they propagate into the atmosphere, they're going to have interactions with the atmospheric particles like the nitrogen, oxygen, H2O. They're going to have interaction. So they generating oxygen, OH, oxygen, the nitrogen's chemical species, like they're doing that one, right? Now the distribution and the peaking position along the plasma jet propagation also represent in here. In here, you can see that in this graph, in these figures, like the left-hand side, it is without having the physical ground electrode. That means with the floating electrode configuration. Now comparing to that one, when we have in the additional ground electrode, that means when we're providing the physical electrode in the open air, we can increase the intensity of the chemical species that is generated in the open air, and the peaking of the these chemical species also very smooth in the laminar regime comparing to the turbulent regime. So in the laminar regime, it is showing increase with the flow rate, but with the turbulent regime, they again try to decrease, even though the plasma is showing a the fat plasma, but the species generation is decreasing. So it is very important to identify with this information which type of plasma we should generate to our application. So the voltage effect also I investigate, but what I observe is like the jet length is slightly increased, but for the chemical species distribution, it is not affecting much, right? Then when we identify the plasma jet, which is suitable for our study, then we do the plasma patterning. For the especially the novel approach, we use the mass-free plasma patterning, and we succeed that one. Then in that time also, we also thought that why we not use the plasma patterning. So these results showing that what we have obtained. So we have some dish, the petri dishes, we coated with the PDMS material. Then we identify 5 points. Now in the upper scale, like in the upper up picture, it is like without the mask, and the bottom picture, it is with the mask. So we then, after the plasma radiation, we did some procedures. Then cell seeding was done. Then we included some genetic modification to the cell culture that is we grow. Then using the fluorescence microscopy, we observe the images, right? So when we do this, that cell cultivation, we to cultivate that one, like I told earlier, that we need to make sure that the material should be changed from hydrophobic to hydrophilic. So when do that one, mean the contact angle, the wettability should be increased, or the contact angle should be decreased. So we use some technique like the droplet method in the substrate, and we took the images using the camera. Then we have the image day software they have in that facilities to estimate the contact angle. So with that one, we investigate what happened into the surface modification condition. So after the irradiation, like we collect the data for 5 days, right? So these two graphs are showing for the first 4 hours and for the 5-day time period with the time with the hour readings, like what is happening. What we observe here is like between the 1 hour, like the contact angle is reduced, right? So it is that scale is very suitable. That means after the atmospheric plasma irradiation, if you want to use the cell cultivation, it should be done within the 30 minutes to 1 hour, because within the 30 minutes also, even though the contact angle is very low, there was some chemical species which is reacted with the cell culture, and we saw that they affect into the cell culturing. So their effect is reducing after the 30 minutes. So but before the starting the contact angle increasing, 30 to 1 hour is very suitable. But when we use in the atmospheric pressure plasma for the surface modification comparing to the low pressure, after 5 days time, they also coming back to their normal state. So it is very important to identify, okay, if we're going to use this one for a surface modification or implant some chemical species, okay, what time period it is going to activate, right? So that is what we also investigate. Then here you can see that the cell culturing without the mask, the sizes may be seen as the same size, but if you check the scale, the 1 millimeter scale, the scale is reducing when increasing the time period. So the summary of these thing is showing in the graph. So with the radiation time, when we increase in the exposure time of the plasma, the culturing area is also increasing. And we expect in that one, this happening because of the diffusion of the chemical species generated top of the surface. Yeah, we know the diffusion is happening. So it is coming to a saturation after some length. So after the 120 second irradiation, if we increase more, we also get in the same value. So it is also coming to larger saturation with the longer irradiation time. But in the low irradiation time, we can see that the sizes are reducing. So that we have idea now that controlling the radiation time, we can control the cell culturing patterning sizes also. But compared to the low pressure plasma, we cannot do that one. Right now, this figure is showing about like with the mask, what is going to happen. Like now, what we observe here is like after the irradiation time 30 seconds to higher, it's showing the same size as the mass size. But lower irradiation times, we can get the culturing patterns lower than the mass size. So it is very important finding that we found, because now when we have in the 1 millimeter mask, we were able to having a cell culture of 100 micrometers. So it is uh, very new thing, like because when we having a discussion with the biological bioengineering scientists, like they're saying that the cell culturing areas ranging between 100 micrometers to 10 micrometers to 100 micrometers. So if we can generate the cell cultures in that scale, then for the diseases we can directly replace the bad cell cultures with the new cells. So it is very important findings. Maybe in the coming years, like this kind of technology will be developed more. Now I show up to now, like what is the plasma, how to generate that one, and the to win for application, for my application, how I investigated about the plasma, what type of plasma generation method I'm going to use, and how what parameters, and with that one what type of information I'm going to get, and the how I succeed my application. Now let us come to the important part. What is the use of atmospheric pressure plasma in Sri Lanka? Because it is very important. Like normally in our country, we are not aware about this technology. Few scientists, yeah, they know about that one, but I still not have any interaction with the Sri Lankan academic or in the research field that using of the atmospheric pressure plasma with the application. But we can use that one in a wide range of applications, such as environmental pollution. The companies like they having that they emitting the toxic gas or the carbon dioxide, they having the problems. But the countries like Thailand, Japan, like now they changing their factories with the this plasma technology to make the toxic air to a non-toxic gases. So the air pollution can be reduced, the waste pollution can be reduced. So that is one of the area that as an industrial application, if we can study this plasma technology, we can go for industry and say, okay, why you guys not use the plasma technology and make the environment pollution to lower level? They will also will be very happy. Then we are talking about the agriculture. We need the nitrogen enrichment. If you saw my previous results, like I saw that the nitrogen, the species also generated, excited species and reactive species also generated. So why we not using that one with our materials? Why we want to depend on the inorganic materials or the fertilizers with the agriculture? We can reduce that one. Then the health issues, like we know we having the problem with the arsenic, like using the clogging or the synthesis, which is done using the plasma technology. We can investigate this parameter. And the low cost sterilization process we can develop, like using the reactive species in the open air without the temperature rising, right? We can make the chemical reactions and we can make the bacterial diffusion, like we can destroy the bacteria. So with the sterilization processes can be introduced, and we can try new type of cell culturing. We can try new type of medicines using the cell culturing while using this technology, make the surface modification. So we can open our country to this area. So here I'm going to discuss a little bit about areas and the problems that we can use, and also some of the published articles, right, about these things. For the pollution, like we know that carbon dioxide and the toxic gases are there. Now, according to the central bank reports, like for the 2021, like air pollution is consist of the composition like this. So for the power generation in or in the industry, waste burning areas, if we can introduce with the plasma technology along with the biomass burning, like we can make the carbon dioxide turning into a carbon monoxide, and then we can investigate new areas which is making the new type of environmental friendly gases. So toxic gases can be removed, and also treating the wastewater, like this kind of studies is happening actually in the world, and in the laboratory which I study, some of Thailand company is funded the money for the Japan, the lab in the Japan. They want to treat the wastewater using the plasma technology. So having that wastewater travel through a plasma discharge, what they achieve is they separate the toxicity of the water from that wastewater. So it is very good application. So in our country also we can use that one. The industry need that one, but normally at the moment also we are using the inorganic chemicals. Normally we are using the chemicals to make such reaction. Because of that one, the use of the chemicals and the money spending on the chemicals is increasing. So this is what is happening with the carbon dioxide conversion. Like if we have in the carbon dioxide, yeah, using the plasma setup, which is showing in the upper figure, like we can discharge it into a carbon dioxide into a carbon monoxide, and also we can generate the oxygen species. So with that one also we can get oxygen species. So we can make, using the carbon monoxide, we can use that one as another gas for making the plasma discharge. So we can make it to a cycle. So it is going to be a sustainable cycle. So we are getting the carbon dioxide and we separated carbon dioxide and carbon monoxide, which is we were able to use as the working fluid in the plasma discharge again. And again, it is making to generate more and more oxygen species. So we can try that one in our country using this conversion. So some of the papers like yeah, I was showing in here. So if the scientists in our country want to investigate this matter, like, yeah, they can refer these articles and can bring this technology to our country, right? Then the biggest problem now we're having with our farms, agriculture field, we need the fertilizers. We are telling why we need the fertilizers. We need the enrichment of the nitrogen. Then because like normally we are using the inorganic compounds to give the more nitrogen enrichment to our soil. Then the government changed that policy into organic compound, but the organic compounds, they doesn't have enough nitrogen. So the provision is not enough. Then we are hearing through the news that the nano urea, like using the nanoscale nitrogen, we try that one, try to increase the enrichment of the nitrogen in our crops. It is not happening. But the previous slides I'm showing that in the open air, because we have in the more than 70% of the nitrogen, we can make it into a nitrogen reactive and the excited species. Then why we not included those things with the organic inorganic compounds? Why we not use the plasma activated water with our these things? Then we can get a high yield of the crop. But the now at the moment with the information that I have, with the interactions I'm having, the South Korea and the Netherlands, they investigate in these matters very thoroughly, like they're giving more weight, right? So how to use the open air as a country. So we can, if we can bring this technology, we can reduce the amount of money that we're going to give it to the outside or the out of the country. We can save our dollars inside of the country. So the technology, the mechanism of this one is like in the water or the open air. Yeah, here you can see that where the discharge materials interact with the nitrogen, they generate in the nitrogen ions or the excited nitrogen into ions. Like we can generate those species. Those species can enrich the compounds. So if we can have the organic compounds and if we can open it into the plasma, open air or the atmospheric pressure plasma, if we can enrich the nitrogen content, I think we can have a method to save the money and also improve the agriculture section in our country. So the some of the studies about the enrichment of the fertilizers or the using with the food about this atmospheric pressure plasma is listed in here. Like if you want to discuss more, like you can contact me. I will give you more information. Then this one also, like again, the South Korea, Japan, and also in the Finland, and they investigating like the floating farming technologies they investigating. So with that one, they investigating, can we use the plasma activated water? Because when we activate it with the plasma, it can enrich the reactive and the charged species. So with that one, like it can help the plants to grow. It can help to control the pH values, right? So some of the studies also they're showing some succeed with these kind of things. Then the particle synthesis or the clogging also can be done. In here, it is one of the study parallel to my study which is happening. So in here, we investigated for the gold, silver, and for the platinum, like we able to make the nanoparticle synthesis. So the solution which is mixed, we able to make the clogging. So why? If the plasma technology can able to make the clogging, why we not investigated with the arsenic? Arsenic is also kind of a metal type material. So if we can use that one with the plasma technology, maybe we can make a synthesis or the clogging, right? Then maybe we can deposit the arsenic in the from the water. So the farmers will be removed from the arsenic problem. So there will be also some studies representing with such synthesis or the clogging using the atmospheric pressure plasma technology, right? So I will come to the conclusion, right? Atmospheric pressure plasma able to generate reactive and excited chemical species in the open air. So it is very important. Without using external chemical species, we can use the open air chemical species, right? So we can use that one for the surface modification to biomedicine area. It is low cost product and easy to handle, right? And in our country also, in a various field, it can address us. So from this conclusion, I'm going to stop my talk. Like, so thank you. Let's hope we will also work and we will able to make a new interest of this field and make a new applications using the atmospheric pressure plasma in Sri Lanka. So if you have any questions, any clarification you like to know, please feel free to ask.
Dr. Leon, thank you very much for your nice presentation and introducing nice technology to Sri Lanka. So I would like to know what are the challenges to implement this technology in various fields. Let's assume in the agriculture field, what are the major challenges in Sri Lanka?
Yeah, thank you for the question, Dr. Vasanti. The main challenges is like now for my app, like using the atmospheric pressure plasma, we know that yeah, nitrogen species, the reactive species can be generated. But if you're going to use the enriching the nitrogen in the fertilizers that we're going to use with the agriculture, then we need to know, okay, how long it is going to sustain with the organic or the inorganic compound that we're going to use, and which length, okay, the species with the technique the plasma going to generate it, like which position we going to uh, place, or the we open it or treat it samples, like in which place we should keep these materials for the enhancing the nitrogen species. We need to investigate that one. And also like uh, uh, nitrogen species like enrichment for a, how to say, like for the open air, or if we included with another air with an admixture, which composition we were able to give us the most enrichment of the fertile nitrogen species to the enrichment, to the fertilizers, we need to investigate. So I think if we start at the moment, like within 2 year time, like we will able to achieve that targets.
Thank you very much, Dr. Lima. Yeah. It seems we don't have any questions further to clarify. So let's move into the conclusions of the day. So anyone volunteer to give the thank you speech for on behalf of Dr. Liam Fernando?
Yeah, thank you, madam. Sorry, can you hear me?
Oh yeah, we can hear you.
So even we heard about that there is a state called plasma, and we had some little bit knowledge about what are the things we can do with those things. I think all of my batchmates also some kind of new for this field. So I guess that is why they are having some silence in this session. I think, but after this session, they will try to search or research about so many things about this. I think that this session make show us some another path, another field that you can go, some another new path you can go for that. So hope all of my friends having wonderful and valuable evening session today. So I like to give my heartful gratitude to Dr. Leon Fernando, Senior Lecturer at Department of Physical Sciences and Technology, Sabaragamuwa University of Sri Lanka, for conducting such an informative session. And I like to thank Dr. Vasanthi D. Silva, who represents the Sri Lanka Association for Advancement of Science for Corporate for Science for Corporate in this session. And I like to thank all of you, all of sorry, thank all for your participation in this very first session, which we collaborate with the SLAAS section E1. And I think as a Society of Technological Studies, we hope to do collaborate with the SLAAS section E1 for more further sessions. So I thank you again, all of you, for make this evening wonderful. Thank you.
Thank you very much. So I also like to thank for the Dr. Vasanthi De Silva for giving me opportunity to introduce my study, and for the SLAAS also, like as an association, like making a platform to increase the interest about the new areas of the scientific knowledge. And thank you very much for the student association of the in the physical science and technology department for collaborated with the SLAAS and making this session possible, and all the participants also like listening to this new area of the study. And I hope you will have more interactions and more findings, or more searching about this area, and you will become the pioneers in Sri Lanka to developing the new applications using this technology. So thank you very much, and good night to all of you.
Good night, Dr. Leon and all.